Now we are moving into the definition of probability. Definition of probability. It's a very important definition because the probability theory goes with the definition of probability. Let omega be a sample space. Let F, capital F, be a sigma field over omega a real valued set function that is P defined on F satisfying the first condition, that is P of A greater than or equal to 0 for all A belonging to F. The first condition is P of A greater than or equal to 0 for all A belonging to F. The second condition, P of omega is 1. Third condition, if A1, A2 and so on are mutually disjoint events. I have not said what is the meaning of events, I will discuss event later. Mutually disjoint events in F, then the P of union of Ai's over I, that is same as summation P of Ai's over I. Basically a real valued set function P defined on F satisfying these three conditions, that is called a probability called a probability. The triplet, that is omega F capital P, that is called a probability space. This definition is very important. We have a random experiment. You know what is the meaning of random experiment. That means it is an experiment in which the results are not known in advance. If you collect all possible outcomes of a random experiment, that collection, all possible outcomes, that collection is going to be called it as a sample space, that is omega. From omega, that's a non-empty set obviously. From there we created the sigma field. So you create a sigma field, one sigma field, it could be trivial or non-trivial. You create a sigma field over a non-empty set omega. Now we are going to create a set function, that's a real valued function. That means it is mapping from F to R. The P function is a set function from F to R. F is a sigma field which consisting of subsets of omega satisfying the three conditions of the sigma field. Therefore, the elements of F, that is nothing but the subsets of omega subsets, since it is a subsets of omega, that is called events. So here the A, when I make the first satisfying the condition P of A greater than or equal to 0 for all A belonging to F, so each element of F, that is called event, because that is a subsets of omega. That means a few collection of possible outcomes, that is going to be the event. Even a single element is also single possible outcome, or any possible result, or each sample, that is also called event. For subsets of possible outcomes, that is also going to be called as an event. So here the element of F is called a event, whereas the element of omega, that is called samples. Repeating again, the elements of omega, that is called samples, element of F is called event. We are defining the set function P on F, which is a real valued function, therefore it is a mapping from F to R, satisfying the three conditions. See the first condition, P of A is greater than or equal to 0. That means it is a real valued function and it is greater than or equal to 0, therefore the values are possible values of range of P is going to be from 0 to infinity from the first condition. But if you see the second condition, P of omega is equal to 1. If you recall, F consisting of element starting from empty set, singleton element and all the possible elements and so on, finally you have a omega. The P of omega is equal to 1 makes the real valued set function defined from F to R, which has the range from 0 to 1. It is a real valued function, that means it could be minus infinity to infinity. Since the P of A is equal to greater than or equal to 0, that restricts from 0 to infinity. The second condition, P of omega, that is equal to 1, that makes lies between 0 to 1. Therefore, this domain is F, range of P is between 0 to 1 closed interval. It can start from 0, it will end up 1. Therefore, it lies between 0 to 1. Now, we will come to the third condition. The F consisting of many elements, starting from empty set with the many elements, the last element is omega. So, if you take mutually disjoint events, what is the meaning of mutually disjoint? If you take any two elements, if you go for intersection, that is going to be the empty set. That is called a mutually disjoint event. If you take any two elements in the F, make an intersection, that is going to be the empty set. So, if you take such events, mutually disjoint events, it could be finite elements or countably infinite elements. If you take those elements and you verify P of union of AIs, make a union of those elements, that is also belonging to F because of the sigma field. And the right hand side, if you make a summation of P of AIs, if both the values are going to be same, if this condition is satisfied by taking any mutually disjoint events in the F, then you can conclude the set function P, which has a domain F, range is 0 to 1, that real valued function we call it as a probability. That is a probability. It is very important because the omega be a sample space for a random experiment, whereas you can have more than one sigma field on the same omega. For a fixed F, we are creating a set function that is a one set function satisfying these three conditions, therefore it is a probability. That means we can always create some other set function on the same omega and F. It may satisfy all the three conditions, then we can have another probability for the same omega and F. So many more probability can be defined by satisfying these three conditions for a fixed omega and f. Therefore, this triplet, the omega, the fixed f and the fixed p, this triplet is called a probability space. Because you can have a many probability for a same omega and f, therefore you can have a many probability space can be created for the same random experiment. That is a very important concept in probability. Whenever we come across, whenever we make a real world problem using a probability theory and we are trying to solve it, we should have a one probability space to solve that problem. So that probability space comes from collection of all possible outcomes for a fixed f, then for a fixed p. You can have a different f, you can have a different p, therefore you will have a different probability space. That means the same problem can be solved in a different probability space. That is going to be a very important topic in stochastic calculus or in financial mathematics. People will solve the problem in a different probability space, therefore their results are going to be different based on a different probability space. So here we have a omega and a fixed f, a fixed p, therefore it's a one probability space. There is a one more observation. Since the p is a set function satisfying the first condition and the third condition, therefore this p is called a measure. You can always define a measure on a non-empty set with the sigma field. We should have a non-empty set omega and you create a sigma field on a non-empty set. Then you can define a measure satisfying the first condition and the third condition. Then that is going to be called as a measure. Any set function satisfying the first condition and the third condition is going to be called it as a measure. And here the p is going to be a measure because it satisfies, it coincides the definition of measure. Therefore, the probability, the word p is a probability, we say the p is a measure also. Not only that, by seeing the second condition, it is a additional condition while seeing the concept of measure. It has the value, it cannot cross more than 1. Therefore, it is called a normed measure. Whenever the measure has a finite value, then it is called a normed measure. So here the finite value is 1, therefore it is a special case of measure which is a normed measure. So the probability is a measure, probability is a normed measure because of the second condition. We are going to see different probability for the different omega and f as examples. As a first example, we will take the easiest example, that is omega consisting of h tail, h or t. F we will go for the largest one, that is empty set, singleton element and the whole set. I have to create a function, set function p, such that it satisfies all the three conditions of the probability. Then I can conclude that set function is a probability. Define p of a such that when a is going to be a empty set, I am going to make it a 0, and when a is going to be h, I am going for 1 by 5. When a is going to be tail, it is going to be 4 by 5. When a is going to be whole set one. You can verify whether all the three conditions of probability definition satisfies. It's always greater than or equal to 0, that is satisfied for all elements A belonging to F. That's the first condition. Second condition, P of omega is equal to 1, that is satisfied. If I take a mutually exclusive events in F, then the union of events, then finding the P over the events, that is same as the summation of P of A's. Suppose I take the element H and tail, so if make a union, so that union is going to be omega, and P of omega is 1. In the right hand side, if I take a P of H, that is 1 by 5, P of tail, that is 4 by 5, if I make addition, that is going to be 1. Not only this, if I take any two elements, if I make a union, that is going to be same as P of union is same as the sum of P of A's. For any 2 or 3 or any collection of mutually exclusive events, it satisfies. So since it satisfies all the three conditions, P is a probability. Now we can think of, is there any other function also satisfies the same three conditions, therefore we will have a one more probability. So here this omega f p, that is a probability. So let me go for making a notation called suffix 1. That means p1 is a probability, therefore omega f p1 is a probability space. By seeing these numbers, we can think of, we can change the numbers, still we can have a probability. That is, I will go for immediately P2 of A, that is going to take the value 0, 2 by 5, 3 by 5, 1. The same way, A is equal to H, A is equal to tail, A is equal to 1. That means this is also satisfying the probability conditions, therefore this is also probability space. Is there only these two? We can go for many combination in which I can go for P of A such that it takes a value 0 with some Q, 1 minus Q and 1, where Q is lies between, so this is for A is equal to empty set and A is equal to H, A is equal to tail and A is equal to omega, where Q is open interval 0 to 1, where Q is open interval 0 to 1. That means I can have a many probability, therefore I can have a many probability space for this example. Whatever we discuss in the elementary level, we always go for a fair coin or unbiased coin. In that case, the probability of getting a head or probability of getting tail, or P of A when A is equal to H or A is equal to tail, these values are going to be 1 by 2 and 1 by 2. Then it is corresponding to the random experiment of tossing a fair coin or unbiased coin. So whatever we discuss in the school days or the elementary level, having a probability 1 by 2 and by 2, that is a one of the probability space which we have discussed. But in general, if the coin is not fair or biased coin, we can have a many more probability space for the same example, for by going for a different P. And one more observation, by different F also we can have a different P's, then we can go for different probability space. I have fixed a F here, I am going for different P, but you can change the sigma field, then also you will have a different P satisfying the condition, therefore you will have a different probability space. I forgot to mention this definition is called the axiomatic definition of probability. This definition is called the axiomatic definition of probability. This is developed by the probabilistic person named Kolmogorov. He's a Russian mathematician who contributed quite a lot for probability theory. Therefore, this definition is called Kolmogorov axiomatic definition of probability. And this definition is valid for whatever be the situation you have for a random experiment. This definition is valid. Whereas there is a classical definition of probability, which is a special case of axiomatic definition of probability, that we are going to discuss after a few more examples. This axiomatic definition of probability does not have any assumptions on a random experiment, on omega and f and so on. Whereas the classical definition of probability, which has some assumptions, with that we will go for the easiest definition of probability, that is a classical one. Whereas this one does not have any assumptions, therefore this is in general it is true for any sort of situations where we are going to apply the probability. So this is a very important definition called axiomatic definition of probability. These three axioms are called the Kolmogorov axioms. These three axioms or conditions are called Kolmogorov axioms, and the definition called axiomatic definition of probability. So this is the easiest example in which I have introduced many probability. Therefore, we get the many probability space for a simple example itself. When it is a fair coin, then the P of A is going to be 0, 1 by 2, 1 by 2, 1 for these elements empty set H, tail and omega. Now we will go for the second example, in which we will have a omega consisting of countably infinite elements. So omega is going to have a 0, 1, 2 and so on, countably infinite elements. F is the largest sigma field on or over omega. I am not going to list out the elements. That means it started with the empty set and all single elements, any two elements, any three elements and so on. So that is the largest sigma field on omega. Now we are going to define P of singleton element of samples in the omega itself. That is going to be 1 divided by 2 power w plus 1, where w is belonging to omega. Even though the set function is defined from f to 0 to 1, I am defining for each singleton element in the omega. Therefore, any element in the f is nothing but the subsets of omega, that is a union of a few elements of the omega, that is going to be the element of f. Therefore, the same set function can be defined for the P of A, where A is subsets of f. So this is going to be 1 divided by 2 power w plus 1. Let us have an example. Suppose w is equal to 0. Then the P of 0 is 1 divided by 2 power 1, 1 by 2. Suppose w is equal to 1. Then P of 1 is 1 divided by 2 power 2. that is 1 by 4. Suppose that W is going to be 3, then it is going to be 1 divided by 2 power 4. We can verify whether this is going to satisfy all the 3 axioms of axiomatic definition of probability. So the first condition is going to be greater than or equal to 0. So whatever be the element of W belonging to omega, this value 1 divided by 2 power W plus 1, that is going to be greater than or equal to 0. And P of omega, we can verify the second condition. P of omega, that is going to be same as a summation of P of singleton elements of W's, where W is equal to 0 to infinity. That is same as P of omega, because P of omega is nothing but the union of all the elements. That is same as summation of W is equal to 0 to infinity 1 divided by 2 power W plus 1. So the first element is 1 by 2, second element is 1 by 4, third element is 1 by 8, and so on. If you add all the elements, it's going to be 1. If you take any disjoint, mutually disjoint events, nothing but disjoint samples, and find out the P of union, that is same as a summation of a P of singleton elements. That's the same concept I used it in finding the P of omega also. I have used the P of omega is nothing but the summation of P of individual element. I am using the third property. So third property also satisfied. So all the 3 properties are satisfied, all the 3 conditions or all the axioms are satisfied. Therefore the P is going to be a probability. Therefore omega F and the capital P is a probability space. Again, the way I defined the P of omega is equal to 1 divided by 2 power W plus 1, someone can think why it has to be this number? Can I choose some other number so that I can have all the 3 conditions are satisfied? Yes, you can always create another real valued function so that all the 3 conditions satisfied, we can have a probability. So I have just created easiest one, that is 1 divided by 2 power W I plus W plus 1, because I know that the summation of this is going to be a convergence series, that summation is going to be 1. Therefore I have created a probability over this. We will go for the third example, that is omega consisting of uncountably many elements, that is 0 to infinity. So the sigma field, that is a Borel sigma field on the real line which intersect 0 to infinity, correct? Creating a Borel sigma field on a real line intersecting with 0 to infinity, that is going to be the largest sigma field on omega, where omega is 0 to infinity. I am going to define a set function P such that this is going to be the probability. The easiest one, that is integration over a e power minus x dx, where a is belonging to f. A is belonging to f. The f consisting of a singleton element, empty set, singleton element, and many intervals between 0 to infinity, which is in the same form of Borel sigma field on real line. Therefore, the integration over a, that is a Riemann integral. You know that if a is going to be a singleton element, that is going to be 0. if A is going to be a closed interval or open interval, because it's a Riemann integral, the answer is going to be integration over that interval e power minus x dx. So always the first condition is going to be satisfied, that is P of A is always going to be greater than or equal to 0. The second condition we can verify P of omega, that is nothing but integration over omega e power minus x dx, that is nothing but x y e power minus x. So it start from 1, so this is a e power minus x, integration over omega is from 0 to infinity, so 0 to infinity e power minus x dx is nothing but area below the curve e power minus x between the interval 0 to infinity. It's asymptotically 0 at infinity, so if you find the area, that is going to be 1. The third condition, if you take a mutually disjoint events in F, that is nothing but if you take a non-overlapping intervals and find the area in those intervals and find out the interval separately and sum it up, both are going to be same. Whether you go for union of non-overlapping intervals, find out the P, or finding out individually and sum it up, both are going to be same for any mutually disjoint events, that is nothing but the intervals. So the third condition also satisfied, therefore we can conclude this P is going to be a probability. We can have many more P for the same omega and F. So this is the easiest one, omega, F and P, that is a probability space. With these three examples, one is with the finite, other one with the countably infinite elements, and the third one with uncountably many elements of omega, we have created a different function P and we got the probability space.